universe stretches beyond the boundaries of human comprehension, a cosmic ocean of endless wonders and profound mysteries. From microscopic quantum particles to colossal galactic structures, space unfolds in a display of phenomena that challenge our understanding of existence. Across the observable universe, over 2 trillion galaxies paint an intricate tapestry against the cosmic void, each one housing hundreds of billions of stars in an eternal cosmic dance. Stellar light travels vast distances through space and time, carrying ancient messages from distant cosmic shores. These photons journey through the darkness for thousands, millions, or even billions of years before reaching Earth. Each beam of light tells a story of stellar birth, cosmic transformation, and the endless cycle of stellar evolution that shapes our universe. In the depths of space, stars forge the fundamental elements of existence. Through stellar nucleosynthesis, these cosmic furnaces create the building blocks of matter. Every atom of calcium, iron, and carbon originated in stellar cores, scattered across space through spectacular supernovae explosions. These stellar remnants, drifting through the cosmic void, eventually coalesce into new stars, planets, and all the matter that exists in the known universe. Our solar system emerged from these cosmic processes approximately 4.6 billion years ago. A vast molecular cloud, disturbed by ancient stellar explosions, began a gravitational collapse that would form our Sun and its family of planets. This stellar nursery demonstrated the precise balance of fundamental forces that govern the cosmos. Gravity orchestrating planetary orbits, electromagnetic forces powering the Sun's endless fusion reactions. The scale of the universe defies human perception. Astronomical distances, measured in light years, reveal a cosmos of incomprehensible vastness. The Milky Way alone spans 1,000,000 light years, yet represents just one galaxy among billions. These enormous distances create a unique relationship between space and time. Peering into the depths of the universe means looking back through cosmic history, observing light that began its journey in the distant past. Throughout the cosmos, mysterious dark matter and dark energy dominate the universal composition, yet remain largely unexplained by modern science. These invisible cosmic components shape the largest structures in existence, influencing galaxy formation and driving the acceleration of cosmic expansion. Their presence reveals the depth of mystery that still pervades our understanding of the universe. Extreme environments across space challenge the boundaries of physics. Neutron stars compress matter into states impossible to replicate on Earth, while black holes create regions where space and time curve beyond recognition. Quantum mechanics and general relativity unveil a reality far more extraordinary than human intuition suggests, pointing to a universe governed by laws that often seem to transcend common understanding. The cosmic web weaves an intricate network of matter and energy throughout space. Massive filaments of galaxies stretch across hundreds of millions of light years, forming the largest known structures in the universe. These cosmic highways guide the flow of matter through space, creating a grand architecture that continues to evolve through cosmic time. New stars emerge from vast clouds of gas and dust, while ancient stars reach spectacular ends in tremendous explosions. Nebulae serve as stellar cradles, nurturing the birth of new solar systems in their luminous depths. Supernovae explosions scatter heavy elements across space, continuing the cycle of stellar evolution that has persisted since the earliest epochs of cosmic history. As exploration of these cosmic phenomena begins, each discovery adds another piece to humanity's understanding of the universe. From the planets of our solar system to the most distant galaxies ever observed, space reveals itself as an endless frontier of discovery. The cosmos exists in a state of perpetual transformation, where past and present blur together in an eternal dance of creation and destruction. Beneath the apparent chaos lies an underlying order. a set of fundamental laws that govern everything from the smallest subatomic particles to the largest galactic clusters. These laws write the cosmic story in a language of mathematics and physics, creating patterns that repeat across all scales of existence. From the spiral arms of galaxies to the orbital paths of planets, the universe demonstrates an inherent harmony that connects all cosmic phenomena. The journey through cosmic space reveals a universe more extraordinary than any human imagination could conceive. As understanding of these cosmic wonders unfolds, the true nature of reality emerges, a tapestry of interconnected phenomena that spans the entire history of existence. From the first moments after the Big Bang to the present day, the cosmos continues its endless evolution, writing new chapters in the greatest story ever told. The cosmic origins. The universe's story begins with a moment so profound that it challenges the very limits of human comprehension. The Big Bang. Nearly 13.8 billion years ago, all the matter, energy, and space-time that now make up the cosmos were compressed into a singular point of unimaginable density and temperature. In an instant, this singularity erupted, unleashing the primordial energy that would shape the vast expanse we now call the universe. This wasn't an explosion in the conventional sense. The Big Bang wasn't a detonation within a pre-existing void. It was the expansion of space itself, a rapid inflation that stretched the fabric of the cosmos. Within a fraction of a second, the universe grew exponentially, swelling from subatomic scales to incomprehensibly vast dimensions. This inflationary epoch set the stage for everything to come, laying down the foundation of cosmic structure that would evolve over billions of years. The first moments, a sea of particles. In the beginning, there was a moment so fleeting, so profound, that its echoes still ripple across the fabric of the universe. This was the dawn of time itself, the birth of the cosmos from a singularity, a point of infinite density and unimaginable heat. In that first breath of existence, the universe wasn't merely born, it erupted, expanding with such velocity that the very fabric of space-time stretched faster than the speed of light. This expansion was not into an empty void, it was the creation of space itself, a growing canvas where the grand masterpiece of the cosmos would unfold. The universe, now a trillionth of a second old, was a churning sea of pure energy. At temperatures exceeding a quadrillion degrees, particles as we know them could not yet exist. Instead, the cosmos teemed with a primordial soup of quarks, gluons, and photons, fleeting, restless entities engaged in a chaotic dance. These fundamental particles, the most basic building blocks of matter, collided and annihilated each other in a frenzy of creation and destruction. A cosmic symphony of energy and potential. As the universe expanded, it began to cool. Within mere microseconds, quarks found their companions, binding together to form protons and neutrons. These particles, though small, represented the first stable matter in existence. They were the seeds from which galaxies, stars, and planets would eventually grow, a testament to the transformative power of the universe's earliest moments. Yet, even as matter began to form, the universe was a place of extraordinary simplicity. No atoms, no light, no structure, just a formless expanse of particles and energy, governed by the fundamental forces of nature. Gravity, the gentle sculptor of the cosmos, began to exert its influence, pulling matter into clumps and setting the stage for the cosmic drama to come. The strong nuclear force, meanwhile, bound protons and neutrons into atomic nuclei, though full atoms would not emerge for hundreds of thousands of years. During these first moments, a profound balance was struck. For every particle of matter created, an antiparticle appeared, an exact mirror opposite. When these particles met, they annihilated each other in bursts of pure energy. For reasons still not fully understood, the universe favored matter ever so slightly over antimatter, leaving behind just enough particles to form the cosmos as we know it. This asymmetry, though tiny, was the key to existence itself, ensuring that stars, planets, and life could one day emerge. As the universe aged, near seconds old by this point, the sea of particles began to settle. The violent collisions that had defined its infancy gave way to a more orderly progression. Neutrinos, ghostly particles that rarely interact with matter, streamed freely through space, carrying with them whispers of the universe's earliest moments. Photons, too, began their long journey, though their path was still obstructed by the dense plasma of particles that filled the cosmos. The next few minutes were a critical time in the universe's history, a period known as Big Bang nucleosynthesis. During this epoch, the first atomic nuclei were forged. Hydrogen, the simplest and most abundant element, is formed in vast quantities, accompanied by smaller amounts of helium and trace amounts of lithium. These elements, created in the universe's fiery cradle, would become the foundation for all future stars and galaxies. Though the universe's temperature and density had decreased significantly, it was still a place of extremes. The forces shaping it were unimaginably powerful, yet their effects were delicate and precise. A fraction of a percent difference in the strength of the nuclear force, for instance, could have prevented the formation of atoms entirely. This fine-tuned balance speaks to the inherent harmony of the cosmos, a subtle interplay of forces that allowed complexity to emerge from chaos. By the time the universe was 3 minutes old, its fate was largely sealed. The basic elements of matter had been created and the cosmic story was set in motion. Yet it would take hundreds of thousands of years for this matter to cool and coalesce into the first atoms, and billions of years more for stars, planets, and galaxies to form. Even now, billions of years later, we can trace the echoes of these first moments. The light from the Big Bang, stretched and cooled by the expanding universe, still permeates space as the cosmic microwave background. It is a faint, ancient whisper, a relic of a time when the cosmos was young. To gaze upon it is to look back through time itself, to witness the very beginnings of existence. In these first moments, the universe was a place of profound simplicity and boundless potential. It was a sea of particles, a canvas of energy, and a stage for the cosmic play that would unfold over billions of years. From chaos came the order, from simplicity came complexity, and from the smallest of particles came the grandeur of the universe we see today. Light and matter, the formation of atoms. The universe, once a chaotic sea of particles, continued its gradual transformation as it expanded and cooled. By the time it was about 300,000 years old, a profound change swept across the cosmos, a shift that would allow light to travel freely for the first time, illuminating the vast expanse of space. This epoch, known as recombination, marked a turning point in cosmic history and gave birth to the universe as we recognize it today. In those early years, the universe was still a dense, hot plasma of charged particles. Protons, electrons, and a scattering of light atomic nuclei formed during Big Bang nucleosynthesis. Photons, the particles of light, found themselves trapped in this dense fog, constantly scattering off free electrons in a never-ending interplay. The universe, though filled with light, was opaque, like a thick, impenetrable cloud. But as the cosmos expanded, it cooled steadily, and this cooling unlocked a vital transformation. When the universe reached a temperature of approximately 3000 Kelvin, the relentless energy of photons diminished enough for protons and electrons to combine, forming neutral hydrogen atoms. For the first time, the particles that once roamed free were bound together, creating the building blocks of matter. This transition signified the birth of structure in the cosmos, a precursor to the galaxies, stars, and planets that would later emerge. The formation of neutral atoms brought about a remarkable consequence. Photons were no longer trapped. With no free electrons to scatter them, light was liberated, spreading outward in all directions. The universe, once shrouded in darkness, became transparent, and the first light to traverse the cosmos began a journey that would last billions of years. This ancient light is what we now observe as the cosmic microwave background, CMB radiation, a faint, omnipresent glow that holds the story of the universe's infancy. The cosmic microwave background, a window to the past. The CMB is more than just the afterglow of the Big Bang. It is a time capsule, a direct link to the universe's early moments. It carries with it the imprints of the tiny density fluctuations that existed in the primordial plasma, subtle variations that would later grow into galaxies, clusters, and the vast cosmic web. To study the CMB is to read the blueprint of the universe, to unravel the mysteries of its origins and evolution. Modern telescopes have mapped the CMB with exquisite precision, revealing its delicate ripples and temperature differences of just a few millionths of a degree. These variations, though minuscule, are profound. They mark the regions where matter was slightly denser, where gravity would eventually pull particles together to form the first stars and galaxies. Every ripple in the CMB is a whisper from the cosmos, a testament to the delicate balance that has guided its growth. When you gaze at the CMB through the eyes of science, you are looking back in time to when the universe was only 3,800,000 years old. Every photon of this ancient light has traveled billions of years to reach us, crossing an ever-expanding expanse of space. These photons have seen the birth and death of stars, the collision of galaxies, and the formation of planets. They are messengers from a time long before life existed, carrying the story of the cosmos in their ancient glow. The universe's first atoms, a foundation for creation. With the formation of neutral hydrogen, the universe entered a new era, one of profound simplicity, yet immense potential. Hydrogen, the simplest of elements, became the universe's most abundant building block, a versatile atom that would later fuel stars and form the molecules essential for life. Helium, the second most abundant element, also played a crucial role, particularly in the early formation of stars. These first atoms drifted through the cosmos, pulled together by the gentle hand of gravity. Over millions of years, they began to collect into denser regions, sowing the seeds of the first galaxies. These simple structures would eventually give rise to the complex and awe-inspiring forms we observe today, from spiral galaxies like the Milky Way to massive elliptical clusters spanning millions of light years. The universe, now transparent and filled with neutral atoms, was a place of profound calm. The violent interactions of particles that had defined its infancy were replaced by a serene expanse of hydrogen gas. Yet, beneath this tranquility lay the potential for dramatic transformation. The tiny density fluctuations imprinted in the CMB hinted at the dynamic future of the cosmos, where matter would gather, collapse, and ignite to form the first stars, a universe illuminated by light. The liberation of light during recombination was not merely a scientific event. It was a moment of profound beauty. For the first time, the universe's radiance was free to travel unimpeded, a herald of the cosmos's boundless potential. This light, though faint and stretched by billions of years of expansion, still illuminates the universe today, offering a glimpse into its earliest chapter. Even now, the CMB serves as a cosmic backdrop to all we see. Its faint glow is a reminder that the universe, vast and complex as it may be, emerged from humble beginnings. The photons we detect today are ancient travelers, older than the Earth, the Sun, or even the Milky Way. They are a bridge between the past and the present, a constant reminder of the universe's extraordinary journey. In the vastness of space where galaxies drift like islands in a cosmic ocean, the light of recombination is a beacon of the universe's unity. It speaks to the interconnectedness of all things, from the first atoms to the intricate web of life on Earth. It reminds us that we are part of a grand story, one that began with the simplest of elements and continues to unfold in the stars above. The formation of atoms was not the end of the universe's journey, but the beginning of its great transformation. It set the stage for everything to come, from the first stars to the galaxies that fill the night sky. In this light, we see not just the past, but the promise of the future, a universe forever evolving, forever creating, and forever inspiring. The cosmic dark ages. In the wake of recombination, the universe entered a profound silence, a period known as the cosmic dark ages. The glow of the cosmic microwave background had faded into a faint whisper, and the first atoms, newly formed, drifted quietly through an immense, featureless expanse. No stars twinkled in the black void. No galaxies adorned the night. It was an era defined by darkness, a universe waiting to awaken. The neutral hydrogen gas that now dominated the cosmos was a veil, absorbing the light from newly freed photons and rendering the universe opaque to visible light. These simple hydrogen atoms, the building blocks of all that would follow, spread out across an ever-expanding sea of space. For millions of years, this fog of gas remained still, untouched by the light of stars or the glow of galaxies. Yet, beneath this seeming emptiness, the seeds of cosmic creation were germinating. The gentle sculptor, gravity at work. During these dark ages, gravity took center stage, quietly shaping the future of the cosmos. The faint ripples in the density of matter, subtle imprints left by the early universe's quantum fluctuations, began to grow. Regions with slightly more matter exerted a stronger gravitational pull, drawing in surrounding gas and dark matter. Over time, these denser regions became the cradles of the first cosmic structures. Dark matter, an invisible and mysterious substance, played a crucial role in this process. Unlike ordinary matter, dark matter did not interact with light or electromagnetic forces, allowing it to form dense halos unimpeded by the heat and pressure that affected baryonic matter. These halos acted as scaffolding, guiding the formation of gas clouds that would eventually collapse to form the first stars and galaxies. As gravity continued its slow but steady work, the universe began to break its symmetry. What once appeared as a uniform expanse became punctuated by regions of increasing density. These clumps of matter, though still faint and diffuse, marked the first steps toward the cosmic web, a vast and intricate network of filaments and voids that defines the universe today. The quiet builders, neutral hydrogen clouds. In this era of darkness, neutral hydrogen gas was the protagonist. These atoms, formed during recombination, filled the universe in a delicate balance. They were both the architects and the obstacles of the coming light. Their presence allowed the universe to cool and stabilize, but their ability to absorb ultraviolet radiation meant that any nascent sources of light were quickly smothered. Neutral hydrogen also acted as a cosmic thermometer, its gentle vibrations revealing the temperature of the universe during this time. Astronomers today can study the faint signals of this hydrogen, specifically its 21-centimeter emission line, to piece together a picture of the Dark Ages. This signal, though incredibly weak, provides a rare glimpse into a time when the universe was veiled in shadow. The first sparks, preparing for light. While the cosmic Dark Ages were marked by silence, they were far from static. The universe's continued expansion allowed temperatures to drop further, and the clumps of matter pulled together by gravity grew denser. Within these regions, the conditions for the first stars were slowly coming into place. As gas accumulated in these gravitational wells, it began to collapse under its own weight. The compression caused by this collapse generated heat, raising the temperature at the cores of these gas clouds. Over millions of years, the cores grew hotter and denser, inching closer to the moment when nuclear fusion could ignite. These protostellar objects, hidden within their gas cocoons, were the universe's first tentative steps toward illumination. The Dark Ages were also a time of chemical transformation. While most of the universe consisted of hydrogen and helium, small amounts of molecular hydrogen began to form. These molecules, created by rare collisions between hydrogen atoms, acted as a cooling agent, allowing gas clouds to collapse more efficiently. Without this molecular hydrogen, the birth of the first stars would have been delayed by millions of years, and the universe's transformation would have unfolded at a much slower pace. The cosmic Dark Ages stretched across hundreds of millions of years, a quiet prelude to the universe's grand illumination. During this time, the universe was a paradox, profoundly simple yet infinitely complex, static yet brimming with potential. Every clump of gas and dark matter carried within it the promise of galaxies, stars, and planets yet to be born. It was a time of preparation, a cosmic stillness before the first symphony of starlight. The end of the Dark Ages was heralded by the birth of the first stars, called Population 3 stars. These stars, massive and short-lived, emerged as beacons in the darkness, igniting with the power of nuclear fusion and flooding the cosmos with ultraviolet light. Their light began to ionize the surrounding hydrogen, breaking apart neutral atoms and clearing the fog that had cloaked the universe for so long. This period, known as reionization, marked the dawn of a new era, where light again reigned supreme. The cosmic dark ages were when the cosmos seemed dormant, yet every particle, every atom, was part of a grand design. It speaks to the delicate balance of creation, where even in the absence of light, the forces of nature worked tirelessly to build the foundation for all that would come. To contemplate this era is to gaze into the universe's soul, to see its quiet determination and boundless potential. The Dark Ages were not merely a pause in the cosmic story, but a necessary chapter, a time of preparation and transformation. The first sparks of light would emerge from the Dark Ages, illuminating the path to the universe's breathtaking complexity. Even now, the remnants of the Dark Ages linger in the faint signals of hydrogen clouds, in the subtle patterns of the cosmic microwave background, and in the gravitational waves that ripple across space. They are a reminder of the cosmos' journey from a featureless void to a universe teeming with light and life. The first stars and galaxies. Out of the darkness came light. Nearly 100 million years after the Big Bang, the silence of the cosmic Dark Ages was broken by the birth of the first stars. These ancient giants, known as Population 3 stars, ignited in a blaze of nuclear fusion, heralding the dawn of a luminous new era. Their light pierced the darkness, transforming the universe and setting into motion the processes that would create galaxies, planets, and eventually life itself, the birth of the first stars. The formation of these first stars was a moment of profound transformation. Gravity, the quiet architect of the universe, had spent millions of years sculpting the dense pockets of gas that would serve as stellar nurseries. Within these gravitational wells, hydrogen gas gathered and collapsed, pulled together with relentless precision. As the gas compressed, it grew hotter and denser, until finally, at temperatures exceeding 10 million Kelvin, nuclear fusion ignited at the cores of these protostars. Unlike the stars we see today, Population 3 stars were composed entirely of primordial hydrogen and helium, the only elements forged in the Big Bang. They lacked the heavier elements, carbon, oxygen, iron, that define later generations of stars. This purity gave them unique properties, allowing them to grow to immense sizes, often hundreds of times the mass of the Sun. These stars burned with incredible intensity, their lives measured not in billions of years, but in mere millions. A fleeting moment on the cosmic time scale. As these stars radiated energy, they reshaped their surroundings. Their intense ultraviolet light began to ionize the hydrogen gas around them, breaking apart neutral atoms and creating bubbles of ionized gas. This process, known as reionization, marked the universe's awakening. The fog of the cosmic Dark Ages began to lift, replaced by the clarity of a universe illuminated by starlight. The light of the first stars was not merely a beacon, it was a force of transformation. Their intense radiation heated the surrounding gas, creating pressure that slowed the formation of new stars. Yet their deaths were equally transformative. These massive stars lived fast and died young, ending their lives in spectacular supernova explosions. These explosions scattered heavy elements, carbon, oxygen, nitrogen, into space, enriching the surrounding gas and paving the way for the next generation of stars. These elements, forged in the hearts of dying stars, became the building blocks of planets, oceans, and life. Without the heavy elements created by Population 3 stars, the universe would lack the diversity of matter needed to create the rich complexity we see today. In their brief lives, These ancient stars sowed the seeds of everything that would follow, their light and remnants shaping the destiny of the cosmos. The emergence of galaxies. As the first stars burned and died, gravity continued its patient work. Over hundreds of millions of years, the dense regions of gas and dark matter that had given rise to stars grew larger and more structured. These regions became the first galaxies, collections of stars bound together by gravity and dark matter. These early galaxies were small compared to the majestic spirals and clusters we see today. They were chaotic and irregular, their shapes sculpted by the turbulence of stellar winds, supernova explosions, and the relentless pull of gravity. Yet they were the precursors to all galactic structures, the first steps in the universe's grand architectural evolution. Galaxies grew through a process of hierarchical merging, where smaller structures collided and combined to form larger ones. These cosmic collisions, though violent, played a crucial role in shaping the universe. They stirred gas and dust, triggering bursts of star formation and creating the intricate structures that define galaxies. From these humble beginnings arose the vast and complex systems that dominate the cosmos. From the sprawling spiral arms of the Milky Way to the dense clusters of elliptical galaxies. In the formation of galaxies, dark matter was an invisible yet essential force. This mysterious substance, which interacts only through gravity, provided the scaffolding for galaxies to form. Dark matter halos, vast and diffuse, acted as gravitational anchors, pulling in gas and stars and holding galaxies together. Without dark matter, galaxies as we know them could not exist. The ordinary matter that makes up stars and planets would not have been able to coalesce and persist. Dark matter's influence extends beyond individual galaxies, shaping the large-scale structure of the universe. The cosmic web of filaments and voids that connects galaxies across billions of light years. The cosmic web. As the universe evolved, the small ripples in the fabric of matter, imprinted during its earliest moments, grew into a vast and intricate structure known as the cosmic web. This grand design, spanning billions of light years, is a testament to the subtle but profound influence of gravity and the unseen scaffolding of dark matter. It is the architecture of the cosmos, the framework upon which galaxies, stars, and clusters are arranged, a lattice of light and shadow that reveals the universe's interconnectedness. The cosmic web consists of vast filaments of galaxies, threading their way across space like veins in a living organism. These filaments are interspersed with enormous voids, regions nearly devoid of matter, where the darkness of the cosmos seems most profound. At the intersections of these filaments lie dense clusters of galaxies, bound together by gravity and dark matter, forming the largest gravitationally bound structures in the universe. The role of dark matter. At the heart of the cosmic web is dark matter, the invisible force shaping its form. Though it neither emits nor absorbs light, dark matter exerts a powerful gravitational pull, guiding the motion of galaxies and shaping the universe's large-scale structure. Without dark matter, the cosmic web as we know it could not exist. Ordinary matter, protons, neutrons, and electrons, would lack the gravitational framework needed to form the galaxies and clusters we observe today. Dark matter halos surround galaxies like unseen cocoons, providing the gravitational glue that holds them together. These halos not only stabilize galaxies, but also act as conduits directing the flow of matter along the filaments of the web. In this way, dark matter serves as the silent architect of the universe, its presence inferred from the motions of galaxies and the bending of light across vast cosmic distances. The birth and evolution of galaxies. As gas and dark matter flowed along the filaments of the cosmic web, they gathered into dense regions that became the cradles of galaxy formation. Within these regions, gas cooled and condensed, forming the first stars and igniting bursts of light that illuminated the surrounding darkness. Over billions of years, galaxies evolved, growing larger and more complex through collisions and mergers. These galactic interactions were not merely destructive, they were transformative. The turbulence stirred by collisions triggered waves of star formation, creating bursts of activity that sculpted galaxies into the intricate shapes we see today. Spiral galaxies with their sweeping arms, elliptical galaxies with their smooth profiles, and irregular galaxies with chaotic forms all emerged from the interplay of gravity, gas, and time. The cosmic web is not static. It is a dynamic and ever-evolving tapestry. Galaxies flow along its filaments, drawn together by the inexorable pull of gravity. Gas streams into dense regions, fueling the birth of new stars, while cosmic voids expand, growing emptier with time. This dance of creation and dispersal, of light and darkness, is a reminder of the universe's perpetual transformation. A symphony conducted by the laws of physics and played out across billions of years. Even now, the cosmic web continues to evolve, its filaments stretching as the universe expands. It is a grand and delicate balance, a structure that speaks to the interconnectedness of all things from the smallest atoms to the largest galaxy clusters. To study the cosmic web is to glimpse the underlying order of the cosmos, a reminder that even in the vastness of space there is unity and purpose. The role of dark energy. As galaxies formed and the cosmic web took shape, another force began to make its presence known. A force so mysterious and elusive that it defies conventional understanding. This force, known as dark energy, is the driving force behind the accelerating expansion of the universe. It is a silent but pervasive influence, shaping the fate of the cosmos on the grandest of scales. The discovery of dark energy. The existence of dark energy was first inferred in the late 1990s when astronomers studying distant supernovae made a startling discovery. The universe's expansion was not slowing down as expected, but accelerating. This finding challenged everything we thought we knew about the cosmos, suggesting that an unknown force was working against gravity, pushing galaxies apart at an ever-increasing rate. Dark energy is now understood to make up about 68% of the universe's total energy density. Yet its true nature remains one of the greatest mysteries in modern physics. It does not interact with matter or radiation in any known way, and its effects are only observable on the largest scales, in the accelerated stretching of space itself. Dark energy's influence is both subtle and profound. On smaller scales, within galaxies and galaxy clusters, its effects are negligible, overshadowed by the pull of gravity. But across the vastness of the cosmos, its presence becomes undeniable. It stretches the fabric of space-time, driving galaxies apart and causing the universe to grow colder and more diffuse with time. Some theories suggest that dark energy may be a property of space itself, an intrinsic energy associated with the vacuum of space. Others propose that it may be linked to a new field or particle yet to be discovered. Whatever its origin, dark energy is a reminder of how much we have yet to learn about the universe and the forces that govern its behavior. The future of the universe. Dark energy's influence is not just a force of the present, it shapes the destiny of the cosmos. If the current rate of expansion continues, the universe will grow increasingly empty as galaxies drift farther apart and the light from distant stars fades into obscurity. This scenario, often called the heat death of the universe, envisions a future where the cosmos becomes a cold, dark expanse, a far cry from the vibrant and dynamic universe we see today. Yet, even in this distant future, the universe's story will not end. The particles and energy that make up the cosmos will persist, continuing the cycle of transformation that has defined the universe since its inception. Dark energy, mysterious and unyielding, will remain a silent witness to the unfolding of cosmic time. The story of the cosmic origins is one of unity and transformation, a journey from simplicity to complexity, from darkness to light. It is a reminder that the universe, vast and ancient as it may be, is deeply interconnected. Every atom in our bodies, every photon of light that reaches our eyes, has its origins in the processes that shaped the cosmos billions of years ago. The universe's beginnings were marked by a delicate balance, a dance of forces that allowed complexity to emerge from chaos. From the first moments of the Big Bang to the formation of the cosmic web and the influence of dark energy, the cosmos has evolved in ways that are both predictable and awe-inspiring. To understand our origins, is to see ourselves as part of a larger whole, a thread in the tapestry of existence. It is to recognize that the story of the universe is our story, written in the stars and carried forward by the light of distant galaxies. And as we continue to explore the cosmos, we are reminded that its mysteries are not just out there in the vastness of space, but within us, in the stardust that forms our very being. Stellar phenomena deep in the cosmic ocean, stars undergo transformations that challenge our understanding of physics. Like ancient celestial alchemists, these stellar bodies transmute elements and manipulate the very fabric of space-time. These stellar phenomena represent some of the most extreme environments in the known universe, where matter and energy interact in ways impossible to replicate on Earth. Each stellar object writes its own cosmic story across billions of years, from the violent birth of neutron stars to the reality-bending properties of black holes, all part of an endless cycle of stellar evolution. In the aftermath of massive stellar explosions, neutron stars emerge as monuments to the raw power of cosmic forces. These remarkable objects begin their lives as stars many times more massive than our Sun, burning through their nuclear fuel at a tremendous rate until they exhaust their resources and collapse. The ensuing supernova compresses the stellar core with such incredible force that protons and electrons merge, creating a sphere of almost pure neutrons. These celestial objects compress the mass of several suns into a sphere merely 20 kilometers in diameter, a density so extreme that it strains human comprehension. A single teaspoon of neutron star material would weigh as much as all the mountains on Earth combined, demonstrating the incredible forces at work in these stellar remnants. The surface of these cosmic objects experiences gravity 100 billion times stronger than Earth's, strong enough to smooth out any irregularities larger than the width of an atom. The magnetic field surrounding neutron stars paint invisible but powerful patterns across the cosmic void, exceeding any magnetic force found elsewhere in the universe. These fields, trillion times stronger than Earth's magnetic field, shape the space around these stellar remnants into complex geometries that guide the flow of particles and radiation. Like cosmic sculptors, these magnetic fields create vast structures of charged particles that spiral along invisible lines of force. These cosmic objects' magnetic poles emit radiation beams that sweep through space like celestial lighthouses, creating the remarkable phenomenon known as pulsars. These beams, generated by particles accelerated to near the speed of light, cut through the darkness of space with remarkable precision. Pulsars keep time with an accuracy that surpasses human engineering, rotating with such precise regularity that they rival atomic clocks. As these cosmic lighthouses spin, their beams sweep across space like the hands of a celestial clock, marking time with incredible consistency. Some pulsars spin hundreds of times per second, maintaining their perfect rhythm over millions of years without missing a beat. The fastest known pulsars, called millisecond pulsars, complete several hundred rotations every second, their surfaces moving at speeds approaching a quarter of the speed of light. These cosmic timepieces help astronomers study the fabric of spacetime itself, providing natural laboratories for testing theories of gravity and relativity. The precise timing of their pulses allows scientists to detect even the smallest disturbances in spacetime, including the elusive gravitational waves that ripple through the cosmos. Among the family of neutron stars, magnetars stand as the universe's supreme masters of magnetic force. These rare and extraordinary stellar remnants possess magnetic fields so intense they could strip the information from every credit card on Earth, from a distance halfway to the moon. The surface of a magnetar experiences regular stellar quakes as the immense magnetic forces twist and stress the star's crust. These starquakes release more energy in a fraction of a second than the sun emits in thousands of years, briefly outshining all other sources of X-rays in the sky. The magnetic field of a magnetar is so powerful that it affects the very structure of atoms in its vicinity, distorting electron clouds into cigar-like shapes and making the vacuum of space itself birefringent, splitting light like a cosmic prism. Black holes represent perhaps the most enigmatic stellar phenomena, regions where the familiar laws of physics transform into something almost mythical. These cosmic aberrations form when massive stars exhaust their nuclear fuel and collapse under their own gravitational pull, creating a point in space where gravity becomes so intense that nothing, not even light itself, can escape. At their centers lie singularities, points where known physics breaks down and space-time curves infinitely upon itself. The fabric of space around a black hole warps so severely that time itself flows differently, slowing down as one approaches the event horizon. This boundary marks a point of no return in the universe, a threshold beyond which the normal rules of reality cease to apply. The space around a black hole becomes a cosmic maelstrom where infalling matter heats to millions of degrees as it spirals toward oblivion. Supermassive black holes lurk at the centers of most galaxies, including our own Milky Way, acting as cosmic architects of galactic evolution. These cosmic giants can contain the mass of millions or billions of suns compressed into a space smaller than our solar system. Their immense gravitational influence shapes the destiny of entire galaxies, orchestrating the motion of stars and interstellar matter across vast cosmic distances. The space around these objects becomes a crucible of creation and destruction, where superheated gas and dust form brilliant accretion disks that glow with intense radiation. These disks can spawn powerful jets of particles that stretch for thousands of light years, creating some of the most luminous objects in the universe. Quasars. These cosmic beacons shine so brightly they can outshine their entire host galaxies, serving as cosmic lighthouses visible across billions of light years of space. Binary star systems perform an eternal gravitational dance through the cosmic void, their fates intertwined by invisible forces. These stellar pairs orbit their common center of mass in patterns that range from nearly circular to highly elliptical, creating an endless variety of cosmic choreography. When these stellar pairs include a neutron star or black hole, they transform into cosmic laboratories where extreme physics plays out on a grand scale. Matter flowing from one star to another traces luminous paths through space, forming brilliant accretion disks that glow in X-rays and other high energies radiation. These cosmic transfers can trigger tremendous explosions visible across vast distances, briefly becoming some of the brightest objects in their galaxies. The gravitational forces between binary pairs can distort their stellar companions into teardrop shapes, creating systems where starry tear materials divide from each other in a cosmic display of stellar interaction. Stellar nurseries spread across the galaxy like cosmic gardens, nurturing the birth of new stars within their vast clouds of gas and dust. These molecular clouds, often spanning hundreds of light years, contain the raw materials from which new stars form. Within these cosmic incubators, gravity gradually draws matter together into ever denser clumps, each destined to become a stellar embryo. As these protostellar objects continue to gather mass, their cores heat under the increasing pressure until nuclear fusion ignites, marking the birth of a new star. These regions often contain multiple stellar formations at different stages of development, creating families of stars that will drift through space together for millions of years. The process of star formation sculpts the surrounding nebula, creating stunning structures of light and shadow that reveal the complex interplay between gravity, radiation, and magnetic fields. Wolf-Rayet stars stand as cosmic torches, raging against their inevitable end with a fury that illuminates their surroundings with intense stellar winds. These massive stars, often containing more than 20 times the mass of our Sun, burn so intensely that they blow themselves apart. Their powerful stellar winds, moving at speeds exceeding thousands of kilometers per second, shed their outer layers into space, creating nested shells of ejected material that glow in various colors. These cosmic giants consume their nuclear fuel at a prodigious rate, living for mere millions of years compared to the billions of years smaller stars endure. Their violent deaths as supernovae seed the cosmos with heavy elements essential for the formation of new stars, planets, and eventually, life itself. The nebulae created by Wolf-Rayet stars often take on intricate shapes, forming cosmic bubbles and shells that can span several light-years across, illuminated by the intense radiation from their central stars. Among the most perplexing stellar phenomena are white dwarfs, stars that challenge our understanding of matter itself. These stellar remnants represent the fate that awaits most stars in our universe, including our Sun. What makes white dwarfs truly remarkable is their seemingly impossible nature. They pack roughly the mass of our Sun into a sphere no larger than Earth. This extraordinary density creates a state of matter found nowhere else in the universe, electron-degenerate matter. Within these cosmic pearls, atoms are crushed so closely together that their electron shells collapse. Yet quantum mechanics prevents total collapse. The surface gravity of a white dwarf is so intense that a person standing there would weigh millions of times more than on Earth. These stars no longer generate energy through fusion, yet they continue to glow for billions of years, slowly radiating away their residual heat into the cosmic void. Perhaps even more counterintuitive are the cosmic phenomena known as red giants, stars in their twilight years that seem to defy logical progression. Unlike humans who typically shrink with age, aging stars expand to enormous proportions. When stars like our Sun exhaust the hydrogen fuel in their cores, they begin fusing helium, causing their outer layers to balloon outward until they become hundreds of times their original size. This expansion, paradoxically, causes their surface temperature to cool, turning them red, hence their name. If our Sun were to become a red giant today, it would engulf Mercury, Venus, and possibly Earth, while its outer layers would become so diffuse that they would have less density than a laboratory vacuum. This phase of stellar evolution demonstrates how stars can maintain a delicate balance between gravitational collapse and radiation pressure even as they approach their final stages. The mysterious phenomena of stellar oscillations reveals that stars are not the static, unchanging orbs they appear to be. Many stars, including our Sun, expanding and contracting in complex patterns that can take minutes, hours, or even days to complete. These cosmic heartbeats occur when pressure and gravity engage in a rhythmic dance, creating sound waves that travel through the stellar interior. Some stars, known as Cepheid variables, pulsate with such regular patterns that they serve as cosmic distance markers, allowing astronomers to measure vast distances across space. The relationship between their pulsation period and their actual brightness stands as one of the most important tools in cosmic cartography. In the cosmic wilderness, astronomers have discovered stellar vampires, binary star systems where one star literally consumes its companion. These systems, known as Type Ia supernovae progenitors, consist of a white dwarf slowly stealing material from its neighboring star. As the white dwarf accumulates matter, it approaches a critical mass known as the Chandrasekhar limit. When this limit is reached, the star detonates in a thermonuclear explosion so precise that it can be used as a standard candle to measure cosmic distances. The fascinating aspect of these systems is their predictability. Despite the chaos of stellar evolution, these explosions occur with remarkable consistency, always reaching the same peak brightness. Blue stragglers present another cosmic puzzle that challenges our understanding of stellar evolution. These stars appear younger than their neighbors in globular clusters, shining with a blue brilliance that suggests they formed much later than the rest of their stellar community. However, in these ancient star clusters, all stars should have formed at roughly the same time. The solution to this paradox lies in stellar cannibalism. These stars have essentially found a way to rejuvenate themselves by consuming or merging with their companions, gaining additional mass and extending their lives. This process creates stars that appear to have turned back their cosmic clocks, demonstrating that even in the rigid progression of stellar evolution, there are paths to renewal. The peculiar phenomenon of stellar twins adds another layer of complexity to our understanding of star formation. Some binary stars are so identical in their properties that they appear to have split from a single stellar embryo. These cosmic doppelgangers share nearly identical masses, chemical compositions, and ages, suggesting they formed from the same cloud of gas and dust at precisely the same moment. The precision of their similarity challenges our models of star formation and raises questions about the role of chaos and order in cosmic evolution. These stellar twins often orbit each other in an eternal dance, their gravitational embrace so tight that they will spend billions of years sharing their fate. The nature of time and space. As we journey through the cosmos, the vastness of space reveals not just its wonders, but the profound and intricate nature of time and space themselves. These fundamental concepts, seemingly so intuitive in daily life, transform in the light of cosmic phenomena, where the laws of physics bend and twist, challenging our understanding of reality. This section dives into the mysteries of time and space, exploring their interwoven relationship, the bending of space-time, and the philosophical questions they inspire. Time, the eternal flow. Time as we perceive it is a river, steady, linear, and unyielding. Yet in the universe's grand design, time is far from absolute. It is intertwined with space, forming a four-dimensional continuum that shifts and flows based on gravity and motion. This revelation, first articulated in Einstein's theory of relativity, redefined our understanding of reality and introduced a cosmos where time itself could stretch, compress, and even stand still. In the presence of immense gravity, such as near a black hole, time slows. This phenomenon, known as gravitational time dilation, occurs because gravity warps the fabric of space-time, altering the flow of time relative to distant observers. For an astronaut orbiting a black hole, minutes may pass, while for an observer far away, those same minutes stretch into years. This stark divergence is not just theoretical, it has been observed in satellite clocks, which tick slightly faster than those on Earth's surface due to the weaker gravitational field at higher altitudes. Motion, too, affects time. According to Einstein's special theory of relativity, an object moving at speeds close to the speed of light experiences time more slowly than an object at rest. This effect, called time dilation, has profound implications for space travel. A spacecraft traveling at relativistic speeds could traverse vast cosmic distances in what feels like a few years to its crew, while centuries might pass for those left behind. These insights reveal a universe where time is fluid and subjective, shaped by the observer's position and velocity. The constancy of the speed of light, a central tenet of relativity, ensures that all observers, regardless of their motion, measure the same speed for light. To accommodate this, time and space adjust, preserving the universe's ultimate symmetry. Space, the fabric of reality. If time is a river, space is the stage upon which the universe unfolds. Yet space, too, is far from static. It is a dynamic fabric that bends and curves under the influence of gravity, creating the intricate geometries of the cosmos. Massive objects like stars, planets, and black holes distort this fabric, shaping the paths of objects and light in their vicinity. This bending of space, predicted by Einstein's general theory of relativity, manifests in phenomena like gravitational lensing, where light from distant galaxies is bent and magnified by intervening masses. These cosmic lenses not only create stunning visuals, like Einstein rings and arcs, but also allow astronomers to peer deeper into the universe, revealing galaxies and clusters that would otherwise remain hidden. The dance of space-time. Time and space are not separate entities, but two aspects of the same continuum, space-time. This unification lies at the heart of modern physics, shaping our understanding of the universe's structure and evolution. The curvature of space-time determines the motion of objects, while the distribution of matter and energy dictates the curvature. This elegant interplay is encapsulated in Einstein's famous equation, G is equal to 8 pi t, where geometry and energy are forever linked. The most dramatic manifestations of space-time curvature occur near black holes, where gravity is so intense that space-time folds back upon itself. Here the concept of down loses meaning, and paths that once diverged are brought together in a singularity. These cosmic enigmas are not just fascinating anomalies, they are windows into the fundamental nature of reality, where our understanding of physics reaches its limits. As we gaze into the cosmos, we are not just looking across space, but back in time. Light from distant stars and galaxies has traveled for billions of years to reach us, allowing us to see the universe as it was in its youth. The farther we look, the older the light we observe, until we approach the cosmic horizon, the limit of the observable universe, beyond which light has not had time to reach us. This horizon is a boundary not of the universe itself, but of our ability to perceive it. The universe beyond this limit remains hidden, a realm of speculation and mystery. Yet, the cosmic horizon also reminds us of the unity of space and time, for to see across vast distances is to witness the unfolding of history on a cosmic scale. The bending of space-time gravitational waves. In recent years, the discovery of gravitational waves has provided a new window into the nature of space-time. These ripples, created by the acceleration of massive objects like merging black holes and neutron stars, travel through the universe, stretching and compressing space as they pass. Detected for the first time in 2015 by the LIGO Observatory, gravitational waves confirm Einstein's prediction and open a new era of astronomy. Gravitational waves carry information about events invisible to traditional telescopes. They allow us to hear the universe, capturing the echoes of collisions and cosmic cataclysms that occurred billions of years ago. These waves are not just perturbations, they are the fabric of space-time itself, revealing its dynamic and interconnected nature. The study of time and space is not merely a scientific endeavor, but a philosophical journey. It raises profound questions about the nature of reality and our place within it. If time is not absolute, what does it mean to exist in a universe where every observer's experience of time is unique? If space is dynamic and malleable, what lies beyond its bounds? These questions invite us to ponder the mysteries of existence and to embrace the wonder of a universe that defies easy explanation. They remind us that our understanding is always evolving, shaped by new discoveries and deeper insights. A cosmic perspective, the nature of time and space connects us to the universe in profound ways. The atoms in our bodies were forged in stars that lived and died billions of years ago, their light traveling across space-time to reach us. Every moment we experience, every step we take, is part of the grand dance of space-time, a continuum that stretches from the Big Bang to the distant future. As we explore these concepts, we are reminded of the interconnectedness of all things. Time and space are not merely dimensions of the universe. They are the threads that weave its tapestry, connecting galaxies, stars, and planets to the lives we lead. To study them is to glimpse the infinite, to see the cosmos not as a distant expanse, but as an intimate part of who we are. The nature of time and space. As we venture deeper into the universe's mysteries, the twin concepts of time and space reveal themselves, not as simple absolutes, but as profound and malleable constructs, shaped by the cosmos itself. Time flows and shifts, space bends and twists, and together they create a dynamic tapestry of existence. In this section, we delve into the nature of these dimensions, uncovering their intricate dance, their relationship to gravity and motion, and the ways they redefine our understanding of reality. Time. The eternal flow. Time governs the rhythm of existence, an unyielding force that drives the cosmos forward. It flows ceaselessly, carrying moments into memory and guiding the dance of stars, planets, and galaxies. Yet, on a cosmic scale, time is far from uniform. Einstein's theories of relativity reveal that time is not an absolute but a dimension. Intertwined with space, its flow influenced by motion and gravity. One of the most fascinating consequences of relativity is gravitational time dilation. In regions of intense gravity, time slows down relative to areas of weaker gravitational influence. This phenomenon has been confirmed through experiments involving atomic clocks, which tick more slowly when placed closer to Earth's surface, where gravity is stronger. The implications of this are profound. Near a massive object like a black hole, time could nearly freeze for an observer, while it continues unabated for someone farther away. This means that two observers in vastly different gravitational fields could experience entirely different perceptions of the same moment. Motion, too, alters time. According to special relativity, an object moving at speeds close to the speed of light experiences time more slowly than an object at rest. For astronauts traveling at relativistic speeds, a journey across the stars could span only a few years in their frame of reference, while centuries might pass for those on Earth. This phenomenon, called time dilation, is not merely a theoretical construct. It has practical implications for space travel and our understanding of the universe. Yet the relativity of time invites deeper philosophical questions. If time flows differently for different observers, then what is the true nature of a moment? Is the past truly gone, or does it linger in the fabric of space-time? And if the future already exists as a dimension, what does that mean for free will and the progression of events? These questions remind us that time is not just a scientific concept, but a profound mystery, a bridge between our everyday experiences and the grand mechanics of the cosmos. Space, the fabric of reality. While time flows, space provides the canvas upon which the universe unfolds. At first glance, space seems static, an infinite void in which celestial bodies reside. But space, like time, is dynamic and responsive, bending and warping under the influence of gravity. This malleable nature of space was another revelation of Einstein's general theory of relativity, which described gravity not as a force, but as the curvature of space-time caused by mass and energy. The most striking manifestation of curved space is gravitational lensing, where the light from distant objects is bent as it passes near massive celestial bodies. This bending creates stunning phenomena such as Einstein rings and arcs, where the light from a galaxy or quasar is magnified and distorted by the gravitational pull of an intervening object. These natural lenses not only offer breathtaking views, but also serve as tools for exploring the farthest reaches of the universe, revealing galaxies and clusters too faint or distant to observe directly. On smaller scales, the bending of space explains the orbits of planets and the trajectories of stars. The Sun, for instance, creates a curvature in space-time that keeps the Earth and other planets locked in their elliptical paths. Without this curvature, the intricate dance of celestial mechanics would not exist, and the universe would lack the structure we observe today. Yet space is not merely a passive stage. It interacts with matter and energy, shaping and being shaped in return. The fabric of space stretches as the universe expands, carrying galaxies with it and creating a cosmos that is both ever-changing and interconnected. Even the emptiest regions of space are not truly empty. They are suffused with quantum fluctuations, where particles and antiparticles briefly flicker into existence before annihilating. This quantum foam hints at the dynamic and complex nature of what we might otherwise consider a void. The dance of space-time. Time and space are inseparable. Together, they form space-time, a four-dimensional continuum that serves as the framework for the universe. The curvature of space-time dictates the motion of objects, while the presence of matter and energy shapes that curvature. This interdependence creates a cosmos that is not static, but alive, its structure constantly evolving. The concept of space-time curvature can be visualized through the analogy of a rubber sheet. A heavy object placed on the sheet creates a depression, and smaller objects placed nearby follow curved paths around it. In the universe, this analogy becomes reality. Massive objects like stars, planets, and black holes warp space-time, creating gravitational wells that guide the motion of nearby matter and light. The effects of this curvature are most pronounced near black holes, where gravity reaches its most extreme. Here, space-time becomes so distorted that paths leading away curve inexorably back toward the singularity. This warping is not just a theoretical construct, it is observed in phenomena like the orbits of stars near the Milky Way's central black hole, and the gravitational waves emitted during the merger of compact objects. Einstein's equations describe this dance of space-time with remarkable precision, linking geometry to energy in a simple yet profound relationship. These equations not only explain the universe's past and present, but also provide clues to its future, from the expansion driven by dark energy to the possible ultimate fate of the cosmos. Cosmic horizons, the edge of space and time. As we peer into the depths of the universe, we encounter the profound relationship between space and time. The farther we look, the older the light we see, allowing us to witness the cosmos as it was billions of years ago. This interplay creates the cosmic horizon, a boundary that marks the limits of the observable universe. The cosmic horizon exists because the universe has a finite age, about 13.8 billion years, and light travels at a finite speed. As a result, there is a limit to how far we can see. Light from beyond this distance has not had time to reach us. This boundary is not static, as the universe's expansion continually shifts the horizon outward, revealing new regions of space over time. Beyond the observable universe lies a realm of mystery. The cosmos may be infinite, with regions beyond our horizon hosting galaxies, stars, and phenomena we can only imagine. Yet, the cosmic horizon also serves as a reminder of our connectedness to the universe. The light we see from distant galaxies began its journey billions of years ago, long before Earth or humanity existed, linking us to the cosmos through time and space. Gravitational waves, ripples in space-time. The discovery of gravitational waves in 2015 marked a new chapter in our understanding of space-time. These waves, caused by the acceleration of massive objects, ripple through the universe, stretching and compressing space as they travel. Generated by events like merging black holes and neutron stars, gravitational waves carry information about some of the most violent and energetic phenomena in the cosmos. Gravitational waves were first predicted by Einstein over a century ago, but their detection required technological advances and unprecedented precision. The LightStream-CAT scan, the LIGO and Virgo observatories, have since captured multiple gravitational wave events, transforming them into a new kind of cosmic messenger. These waves allow us to hear the universe, complementing the light we see and expanding our understanding of its dynamic nature. The study of time and space invites us to rethink our understanding of reality. These dimensions, so integral to our existence, are fluid and interwoven, shaped by the cosmos and, in turn, shaping it. They challenge us to consider the vastness of the universe and the intimate ways it connects to our lives. Time and space are not just scientific abstractions. They are the threads of the universe's tapestry, linking galaxies to atoms, stars to the human experience. To explore their nature is to embrace the wonder of existence and to find beauty in the cosmos's profound complexity. From the vast stretches of the cosmic web to the smallest interactions within the fabric of space-time, the universe's complexity offers a wealth of mysteries that spark both scientific inquiry and philosophical reflection. Yet amidst this grandeur, one question lingers. What is humanity's place in this grand cosmic tableau? This section explores how the cosmos shapes our understanding of existence, our technological achievements in exploring space, and the profound questions about life, consciousness, and the universe itself. The pale blue dot, a reflection on Earth's place. In 1990, as the Voyager 1 spacecraft prepared to leave the solar system, it turned its camera back toward Earth, capturing a single frame of our planet Kent, a pale blue dot suspended in the vastness of space. This iconic image, accompanied by Carl Sagan's poetic words, became a symbol of humanity's fragility and interconnectedness. From this vantage point, Earth is but a speck, a tiny haven of life in an infinite void. This perspective humbles and unites us, reminding us of the shared responsibility we bear for our planet and its future. The pale blue dot underscores the rarity of life in the cosmos, and the importance of cherishing the delicate balance that sustains it. The cosmic perspective reshapes our understanding of borders, conflicts, and divisions. From space, there are no nations, no boundaries, only the faint outlines of continents and oceans. This view challenges us to transcend our differences and consider humanity as a single species, unified by its shared origins and destiny. The search for life, are we alone? The vastness of the cosmos raises one of the most profound questions in science and philosophy. Are we alone? With hundreds of billions of stars in the Milky Way alone, each potentially hosting planets, the possibility of extraterrestrial life captures the imagination and drives exploration. Modern telescopes have revealed thousands of exoplanets, many residing in their stars' habitable zones, regions where conditions might support liquid water and, potentially, life. Missions like Kepler and TESS have expanded our understanding of planetary diversity, uncovering worlds that range from scorching gas giants to rocky Earth-like planets. But the search for life extends beyond distant stars. Within our own solar system, promising candidates like Europa and Enceladus, with their subsurface oceans, may harbor microbial life. Mars, too, remains a focal point, with evidence of ancient rivers and lakes suggesting a once habitable environment. The search for extraterrestrial intelligence each broadens this quest, scanning the skies for signals from advanced civilizations. While no definitive evidence has been found, the vastness of the cosmos means that the search has only just begun. Each discovery, whether of alien microbes or advanced civilizations, would redefine our understanding of life's place in the universe and our role within it. Space exploration, humanity's first steps. The journey to understand the cosmos began with a single step: the launch of Sputnik in 1957. Since then, humanity's exploration of space has expanded dramatically, from the first human landing on the moon to the deployment of robotic explorers on distant planets. Space exploration represents the best of human ingenuity and curiosity. The Apollo missions demonstrated humanity's ability to achieve the seemingly impossible, inspiring generations to look toward the stars. Today, missions like Perseverance on Mars and the James Webb Space Telescope, JWST, push the boundaries of what we can observe and discover. The International Space Station, ISS, orbiting 400 kilometers above Earth, serves as a symbol of global cooperation. Astronauts from around the world live and work together, conducting experiments that deepen our understanding of biology, physics, and human adaptation to space. Private companies like SpaceX and Blue Origin have accelerated the pace of exploration, developing reusable rockets and planning missions to Mars. These advancements bring humanity closer to becoming a multi-planetary species, ensuring the survival of our civilization in the face of potential planetary catastrophes. The technological revolution, tools of discovery. Modern technology has transformed the way we explore and understand the universe. Telescopes like Hubble and JWST have unveiled breathtaking images of distant galaxies, while observatories like LIGO detect the faint whispers of gravitational waves. These instruments extend our senses, allowing us to perceive phenomena far beyond human experience. Artificial intelligence, AI, and machine learning have become invaluable tools in sifting through the vast amounts of data collected by telescopes and satellites. These technologies enable astronomers to identify patterns, detect anomalies, and discover new objects with unprecedented efficiency. On Earth, particle accelerators like the Large Hadron Collider probe the fundamental forces that govern the universe, recreating conditions that existed just moments after the Big Bang. These experiments not only deepen our understanding of the cosmos, but also connect us to its earliest moments. The philosophy of exploration. Why do we look to the stars? Beyond science and technology, the exploration of the cosmos touches on deeply human questions. Why do we look to the stars? What drives us to seek knowledge beyond the boundaries of our planet? The answers lie in our innate curiosity and the need to understand our origins and place in the universe. The stars have always inspired humanity, serving as both a guide and a muse. Ancient civilizations used them to navigate vast oceans and construct calendars, linking celestial patterns to the cycles of nature. Today, the same stars inspire dreams of exploration and discovery, reminding us of our connection to the cosmos. This drive to explore also reflects our optimism and resilience. To venture into the unknown is to embrace uncertainty and challenge, to push the boundaries of what is possible. It is a testament to the human spirit, a declaration that we are not content to remain confined to our corner of the cosmos. The fragility of Earth, a cosmic wake-up call. As we explore the cosmos, we gain a greater appreciation for the uniqueness and fragility of Earth. Our planet is a rare oasis in a vast and hostile universe, with a delicate balance of conditions that support life. This perspective is reinforced by images like Earthrise, captured during the Apollo 8 mission, and the Blue Marble, taken by Apollo 17 astronauts. These images reveal Earth's vulnerability and underscore the urgency of addressing global challenges like climate change, resource depletion, and biodiversity loss. Space exploration serves as a reminder of what we stand to lose and the responsibility we have to protect our home. The cosmic perspective also highlights the interconnectedness of life on Earth. From the atoms in our bodies to the water in our oceans, everything originates from the same cosmic processes that shape the stars and galaxies. This unity calls for a global effort to preserve the planet and ensure a sustainable future. Life, consciousness, and the universe. Among the most profound questions raised by the cosmic perspective are those concerning life and consciousness. How did life arise? Is it a rare occurrence or a universal phenomenon? And what role does consciousness play in the universe's unfolding? These questions bridge the gap between science and philosophy, inviting exploration of the conditions that make life possible and the nature of awareness itself. The discovery of life elsewhere, even in its simplest forms, would challenge our understanding of biology, chemistry, and the uniqueness of Earth. The emergence of consciousness adds another layer of mystery, suggesting that the universe not only creates, but also contemplates itself. The cosmic perspective offers both humility and inspiration. It reminds us of our smallness in the grand scheme of things, but also of our capacity for wonder, creativity, and progress. From the pale blue dot to the farthest reaches of space, humanity's journey is one of exploration and connection. A quest to understand the universe and our place within it. As we look to the stars, we are not merely observers, but participants in the cosmos' story. The atoms in our bodies were forged in ancient stars, and our actions today shape the future of our planet and beyond. To explore the universe is to embrace both its vastness and its intimacy, to find meaning in its mysteries and purpose in its beauty.